thank you very much for tuning in to my video. What you are about to watch is really a memorandum for myself. You see, recently I purchased this book, C Programming for the PIC Microcontroller, and one of the problems I have with it is that my learning is not quite at the level to begin comprehending everything written in this book, although the book does say that no prior learning besides C language should be a problem. But anyway, also elusive, and this is going off topic, but Hubert Henry Ward seems to be an elusive character, and I can't find much available on him on the internet. I almost suspect he may not even exist. Maybe I shouldn't say things like that. This book, I haven't completely decided yet whether it's good reading or helpful. I can say that there are a lot of typos, and it didn't get proofread, and the pictures of the software screenshots are not large enough, so it's very aggravating to read this book. But unfortunately, there is limited affordable literature on PIC microcontrollers. So what I am trying to do with this video is just to take concepts and definitions presented in that book, and I've written them down, and then I'm going to try to create almost like a glossary, almost like further reading for this particular book. Now, this video is really for my own sake, so if you are watching it, I hope it's helpful to you. Maybe it will fill in a few gaps. But yeah, it is boring, even for myself. But, well, anyway, I should be more confident. But if you're looking for more entertainment, more better created videos, well, I do have some of those on my channel, so please take a look. Take a look at the most popular videos I have. You might enjoy them more than this one. So yeah, I'm just going to smash and smush a big pile of information together, kind of like an information sandwich, and hopefully it's digestible by the end of it. Alright, so I thought I would begin here with trying to develop a concept of capture and compare. I more or less found this through a Google search, and even at the present time I don't completely get it because it's talking about the different timers, so I'm just going to read the information despite not having a comprehension. Maybe it'll make sense later. Capture, compare, PWM, CCP, enhanced PWM, ECCP, peripheral. And I'll try leaving the link for this in the description below. This is regarding 8-bit MCUs, and it's on the Microchip website. The CCP, ECCP, is a multi-purpose peripheral module inside most of the PIC MCU devices. The module includes 4 unique but related peripherals. Capture mode retrieves a timer value based on a signal event. Compare mode constantly monitors a timer counter value and compares it to a value set in the application. Compare mode will trigger an event when the values match. Pulse width modulation, PWM, produces a variable pulse width signal based on a pulse width and period value set in the application's code. Enhanced pulse width modulation, EPWM, produces a variable pulse width signal based on a pulse width and period value set in the application's code, along with auto shutdown, auto restart, dead band delay, and PWM steering modes. In addition, the EPWM can drive various PWM arrangements: single PWM, half bridge PWM, full bridge PWM, forward mode, full bridge PWM, reverse mode, single PWM with PWM steering mode. So this seems to pertain to a specific chip in a datasheet. I don't even know which one that is. This is on the subject of 8-bit MCUs. The 4 modes of operation are selected and controlled by the Capture Compare PWM Control Register, CCP-CON. CCP times CON, CCPX, Control Register. So I guess in the configuration mode, I guess this is where you set the bits. There's 8 of them. CCP times M, 30 CCP ECCP mode select bits. All modes off. So I guess if you type this code in, I shouldn't speculate, I should just read it. Capture Compare PWM off resets ECCP module. Capture settings, capture mode, every falling edge, capture mode, every rising edge, capture mode, every 4th rising edge, capture mode, every 16th rising edge. Compare settings. Compare mode, toggle output on match. Compare mode, initialize ECCP times pin low. Set output on compare match. Set CCP IF. Compare mode, initialize ECCPX. Pin high, clear output on compare match. Compare mode, generate software interrupt. Only ECCP pin reverts to IO state. Oh, this looks like a good lesson. So I went back to the beginning. This is on microchipdeveloper.com. 8-bit PIC microcontrollers. 8-bit PIC microcontrollers. PIC 10, 12, 16, 18. Okay, here's a chart showing the number of pins. So I guess the 18 series has typically more pins. Okay, 8-bit data, 14-bit instructions, 8-bit data, 16-bit instructions. That's the difference between mid-range and enhanced mid-range and PIC 18 architecture. Easy migration, scale your designs up or down. Performance to meet your application needs, ranging from lowest power up to 100 drystone million instructions per second. DMIPS, complete portfolio from 384 bytes to 512 kilobytes of program memory as your code requirements grow. Upward compatible architecture to preserve investment in code development. Pin compatibility in multiple packages facilitates drop-in replacement from 6 to 144 pins. Self-paced training. There's a really helpful tab on the side here that I've just cut off from recording. I clicked on 8-bit microcontroller summary. 8-bit microcontroller summary. It can be confusing to someone trying to decide the best choice for their product or project, as 8-bit PIC microcontrollers come in several core architectures. This page describes the different options to help you make the correct choice. Baseline 12-bit wide program memory, mid-range 14-bit wide program memory, enhanced mid-range, enhanced 14-bit wide program memory, high-end 16-bit wide program memory. So I'm not making jokes. Like, apparently the difference between the baseline and the high-end is the degree of memory, of program memory. Simple codes, sophisticated codes, I suppose. Here is a chart. Baseline architecture, pin counts 6 to 40, mid-range 8 to 64, enhanced range 8 to 64, PIC 18 architecture 18 to 100. The baseline, there are no interrupts. Mid-range, single interrupt capability. Enhanced mid-range architecture, single interrupt capability without hardware context save. PIC 18 architecture, multiple interrupt capability with hardware context save. Performance, 5 MIPS, 5 MIPS, 8 MIPS, up to 16 MIPS. Instructions, 33 to 12-bit, 35 14-bit, 49 14-bit, 83 16-bit. Program memory, up to 3 kilobytes. Mid-range, up to 14 kilobytes. Enhanced mid-range architecture, up to 28 kilobytes. PIC 18 architecture, 128 kilobytes. I just looked up Arduino program memory size. The Arduino Uno has only 32 kilobytes of flash memory and 2 kilobytes of SRAM. Continuing, hardware stack, baseline architecture, 2-level, 8-level, 16-level, 32-level. Okay, the features of the baseline architecture. It has a comparator, an 8-bit ADC, data memory, an internal oscillator. Mid-range, in addition to baseline, because it has all this, SPI, I2C, UART, PWMs, LCD, maybe a controller, 10-bit ADC, and an op-amp. In addition to mid-range, so I guess it has all this stuff, multiple communication peripherals, linear programming space, PWMs with independent time base. In addition to enhanced mid-range, 8x8 hardware multiplier, it has a CAN, a CTMU, a USB, Ethernet, 12-bit ADC. Highlights: lowest cost in the smallest form factor, optimal cost to performance ratio, cost effective with more performance and memory, high performance optimized for C programming, advanced peripherals. So that was this chart here. The 8-bit PIC microcontroller uses a reduced instruction set computer, RISC architecture, that has a separate address and data bus. This means they can be separate in size as well. All 8-bit PIC microcontrollers have an 8-bit wide data bus, but the program bus will vary in size depending on the family. This can also cause confusion, since the memory structure of an 8-bit PIC microcontroller will be reported in words of a size equal to the program bus, not the data bus. A larger program bus allows the device to place more information in one instruction line and thus more efficient execution. Therefore, memory for each device is reported in words and then a byte reference. I haven't fully got my mind around this, but yeah, I think sometimes things are evaluated in the number of words, word size. I shouldn't comment. For example, an 8K program memory on a 14-bit core device contains 8K words of program space, the equivalent of 14K of space in bytes. All 8-bit devices execute assembly commands in one instruction cycle, except for branches and fetches. This makes for a very efficient operating system. The oscillator speed in most devices is divided by 4 to produce the instruction clock, but enhanced parts have a phase lock loop feature that allows you to step up the oscillator by 4 before the divide to get a 1-to-1 relationship between the oscillator speed and the instruction clock speed. The 8-bit family has some of the lowest current draws in the industry and many features that will run in sleep mode. Well, it would be very time-consuming to try and cover this whole chart, not to mention I don't understand it, but I guess all the different ICs are listed here with the pin counts. Tends to ascend in value. Program flash memory from very small to very large. RAM also, same thing. Data, intelligent analog waveform control, timing and measurement, logic and math, safety and monitoring. Okay, next video. Okay, so further here there's like a table of contents, almost like an encyclopedia, which goes ahead and covers a lot of the technology concepts within these chips. I actually began this video trying to understand capture and compare. Okay, I suppose we can start at the top. ADC, analog to digital converter. The analog to digital converter, ADC, can convert an analog input signal to a 10-bit binary digital representation of that signal. The microchip microcontrollers analog inputs, which are multiplexed into a single sample and hold circuit. The output of the sample and hold is connected to the input of the ADC. The ADC generates the 10-bit binary result via successive approximation and stores the conversion result into the ADC result registers. The ADC uses a voltage reference that is software selectable to be either internally generated or externally supplied. The ADC can also generate an interrupt upon completion of a conversion. This interrupt can be used to wake up the device from sleep. ADC configuration. When the ADC is first set up, it needs to have several configuration settings enabled. These include ADC port configuration, ADC channel selection, ADC voltage reference selection, ADC conversion clock source, ADC interrupt control, ADC result format. We'll step through each of these below. ADC port configuration. The first configuration setting is the I/O pin setup. Most of the ADC I/O pins can be used as either an analog input or a digital input. When converting analog signals using the ADC, the I/O pin must be configured for analog input by setting the associated bits in the trice register and ancel register. The trice register for the I/O pin needs to have its associated bit set to 1 to make it an input. If the I/O pin is part of the port A block, then the trice A register contains the bit. Trice port A tri-state register. Thus, the next step is to set the bit on the ancel register for the I/O pin and set the bit to 1 to enable the ADC on that pin. If the I/O pin is part of the port A block, then the ancel A register contains the bit. ADC channel selection. The ADC multiplexer needs to be connected to the I/O pin prior to starting the sample and hold process. This is done with a set of bits in the ADCON 0 register. Before an ADC sample is requested, these channel select bits are set to connect to the desired I/O pin. Only one pin can be connected to the ADC at a time. After the process is complete, then the selection bits can be changed to connect to the next pin, and the ADC process starts over again. ADCON 0, AD control register 0. Analog channel select bits. ADC voltage reference selection. The ADC can use various voltage reference sources as the basis for analog voltage measurements. Digital value equals analog voltage divided by Vref plus or minus Vref multiplied by 1024. The ADPREV bits of the ADCON 1 register provide control of the positive voltage reference. The positive voltage reference can be Vref, VDD, fixed voltage reference. The AD and Ref bits of the ADCON 1 register provide control of the negative voltage reference. The negative voltage reference can be Vref, VSS. VDD and VSS are the connections to the voltage bus that powers the device. Vref and Vref are specified I/O pins on the device. An external voltage reference is connected to these pins. FVR is a feature on many PIC devices, though not all. It can include a single voltage or sometimes more than one voltage level is available. The voltage reference selection bits are in the ADCON 1 register, and the selection options are shown. ADC conversion clock source. The source of the conversion clock is software selectable via the ADCS bits of the ADCON 1 register. There are up to 7 possible clock options depending on the device being used. FOSC2, FOSC4, and so on and so forth. FRC dedicated internal oscillator. FOSC is the system oscillator that is running the device instruction clock. The clock is critical to producing the fastest but also accurate analog to digital conversion. The time to complete 1-bit conversion is defined as TAD. One full 10-bit conversion requires 11.5 TAD periods as shown here. For correct conversion, the appropriate TAD specification must be met. An ADC clock can be easily selected from the chart below. A similar chart appears in the device data sheet. The values that are the best show up in the middle of the chart in a white background. Phew! Okay, well that's enough for the moment.